All right. So this problem says a 10 amp current flows through the wire shown. So this wire has a 10 amp current flowing through it. What is the magnitude of the magnetic field due to a 0.5 millimeter segment of the wire? So this segment of the wire as measured at point A and point B. I'll find the field at point B, okay? And you can do A is similar. Okay, what is the direction of the field first?
Coming out of the page.
Okay, coming out of the page, okay. Now it's just a matter of figuring out the magnitude, okay? So the expression is given by dB. Why do we write dB? We are saying this is one piece of the field. Why do we write it like that? That's because that's the field due to this piece of wire. And then this piece of wire produces a field there, this piece of wire, and the total field would be the sum of all those fields. Okay, so dB is mu naught I ds cross r hat divided by r square, 2 pi r square. Yeah, let me make sure of the expression. That's the Biot-Savart law.
That was 4 pound the bottom.
Okay, all right, 4 pi. All right, what is the cross product of the vectors? The magnitude of the cross product is magnitude ds, magnitude r is 1, r hat is 1 times sine theta, okay? ds is that, r hat is that, and this is theta. This theta is equal to this theta. Okay, and you can see that that's a right angle triangle. This is 3, 4, and 5. So sine theta is 3 over 5. So this is equal to ds times 3 over 5. Okay, so the magnitude of the field due to that small element is mu times I times 4 pi r square 3/5 times ds. All right, so let me copy this, and that's 0.5 millimeters and so on, okay? Okay, so the magnetic field is mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. I is, the current is 10 amps. 3/5 ds is 0.5 millimeters. R is 5 centimeters. Okay. All right. So the 4 pi cancels. this is 10 to the minus 4 and 10 to the minus 3, 10 to the minus 4. So that cancels that. We'll make that a 5. That 5 cancels that 5. 30. Okay, so 30 into 10 to the minus 7 Tesla divided by 25. And then there was the 3/5 there. No, I took care of that. That's 5 times 10 to the minus 4. The 10 to the minus 4 cancels. This 5 cancels with that. And 30. Okay. I hope I did everything right. And so that is 1.2 into 10 to the minus 7 Tesla. That is the field at that point due to this element. Okay. The field at this point due to this element. Okay. All right. So the figure shows a current loop consisting of consisting of 2 concentric circular arcs. Okay. And perpendicular to radial lines. Okay. Determine the magnetic field at point P. So we want to figure out the magnetic field at point P. What is the field produced by this element at that point? 0. The field produced by this element is 0. Okay. The field produced by this guy, okay, stick your thumb in the direction of the current, and you see this guy will produce a field coming out of the sheet. This guy will produce a field going into the sheet. So this is so the net field is B inner ring minus B outer ring. So what I'm saying is this field, the field produced by this guy is stronger probably because he's closer, even though he's a smaller length. This field, the field produced by this guy probably is weaker. But if I'm wrong, then this will just come out negative, and that means this field is stronger. Okay. So the net field at this point is coming out of the paper if this is larger than that. Okay. Now let's find the field due to this guy. The field due to this guy, okay, so dB inner, let's write dB inner. Let's say this is ds. Okay. There is r hat is mu naught I times divided by 4 pi ds cross r hat divided by r squared. So dB inner is mu naught I 4 pi. Okay. So just the magnitude is, what is ds cross r hat? They're perpendicular to each other. So, and r hat is 1 unit. So this is just ds. The magnitude of that is just ds. And r is a, so a squared. Okay. All right, so we found the field due to this element. Now we want to find the field due to this entire arc. So we just integrate that. So the field due to the inner arc is dB inner equal to mu naught I 4 pi ds over a squared. Mu naught is constant, I is constant, 4 pi is constant, A is constant along those arcs. So we pull them all out. Sum of ds, sum of those little arcs, which is equal to that arc. And so this is equal to mu naught I over 4 pi a squared. And what is the length of that arc? It's 1/4 the circumference, 2 pi a. So the pi cancels, this becomes a half, that becomes 8, one of the a's cancels. So this is equal to mu naught I over 8a. Can you guess what is the field due to the outer arc? Yep, same thing with B. Since B is bigger than A, B outer is smaller. Yep. So the net field is all right. So again, one of the messages of this problem is they gave you that because that integral was easy to do. Yeah. So we do the integral when it's really easy to do and you're not having to really do the integral. You came in by boat, I suppose, I hope? Or it's a long swing home. 40, I had to swim 45 miles. The magnitude of the magnetic field 50 centimeters from a long thin straight wire is 8 microtesla. What is the current through the long wire? Okay. So the field at that point is given by mu naught I divided by 2 pi r. So I is 2 pi r b divided by mu naught. .50 centimeters is 0.5 meters. Eight microtesla. And mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. And you get, when you bring this up, you get 10, so it's 5 times 8 divided by 2, so 20 amps. Okay. A long straight horizontal wire carries a left to right current of 20 amps. If the wire is placed in a uniform magnetic field of magnitude 4 times 10 to the minus 5 Tesla, so this is the Earth's magnetic field, there we go, that is directed vertically downwards. Where is the Earth's magnetic field directed vertically downwards? At the poles, at the magnetic poles. Yeah. What is the resultant magnitude of the magnetic field? 20 centimeters above the wire. 20 centimeters below the wire. We'll just do it below the wire. Okay, so we will even call this the Earth's magnetic field. And what is the direction of the field produced by the wire? Into the sheet below at this point, okay? So magnetic field produced by the wire. Okay. All right, so magnetic field produced by the wire is mu naught I divided by 2 pi r. Okay, so this is, that becomes a 10, that's 200 amps. 200 times that makes it 2 times 10 to the minus 5. Okay. So is 2 times 10 to the minus 5 Tesla. Okay, so this and the Earth's magnetic field are comparable. So about a foot away, the field produced by a 20 amp current and the Earth's magnetic field are comparable. Okay. Now, what is the total field? The total field, so now we'll do so the magnitude of the total field is 16 square root of 20 into 10 to the minus 5 Tesla. Okay. Two long straight wires are parallel and 10 centimeters apart. One carries a current of 2 amp and the other is 5 amps. If the two currents flow in the opposite direction, when the currents are flowing in the opposite direction, what is the force? It's repulsive. Okay. What is the magnitude and direction of the force per unit length? What is the magnitude and direction of the force per unit length if they flow in the same direction? Okay, so I'll just do part A. I1 and I2, and the force is repulsive. Force per unit length is given by mu naught I1 I2 divided by 2 pi, the distance between them. Okay, and let me make sure of the expression. I think it's correct, but yep. So force per unit length is 4 pi into 10 to the minus 7 Tesla meter per amp. Ten centimeters apart. So this is 10, oops. This is 10, and that becomes 100, and that makes it 10 to the minus 5. So 2 times 10 to the minus 5 Newton. Newton per meter. So force per unit length is that. We used to do this experiment in lab. So we'd pass two currents in the opposite direction, and we'd bring the wires real close. And the top wire was supported by the repulsive force, except that the current had to be quite large, and people were burning their hands. So we discontinued the experiment. A flat circular loop has 20 turns. The radius of the loop is 10 centimeters, and the current through the wire is 0.5 amps. Determine the magnitude of the magnetic field at the center of the loop. Okay. So you want to find the magnitude at the center of the loop. Can you tell me the direction of the magnetic field? Stick your fingers in the direction of the current. The magnet points that way, so the magnetic field is like that. Okay. And here's the expression. Let's make sure of the expression. Mu NIR squared 2, okay, there you go. What is Z at the center? Z is 0, okay. And then this becomes R to the power 3, R square cancels, so this is equal to mu naught Ni over 2R. Okay. So B at the center, mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. N is 20 turns. I is 0.5 amps. And R is 10 centimeters. So that's 10 to the minus 1. That makes it 10 to the minus 6. And that is 10. So 10 to the minus 5. So B equal to 4 pi times 10 to the minus 5 Tesla. Okay. So this is about 12, which is about 10 times greater than the Earth's magnetic field. Two flat circular coils, each with a radius r and wound with n turns, are mounted along the same axis. So they are parallel and a distance d apart. Yeah. So that distance is d. What is the magnetic field at the midpoint of the common axis? So we'll call this loop 1, loop 2. If the current flows in the same direction through the coils, I and I. All right, so let's figure this out. Okay, current is like that, and so the magnetic moments point like this. So this acts like north, south, north, south. Okay, there the magnetic field is pointing like this due to this guy, and here the magnetic field due to this guy is pointing like that. The magnetic fields are pointing in the same direction. Okay, B1, B2. So the net field is just B1 plus B2. Okay. What is B? It's, you just saw the expression Ni R square and 2 R square plus Z square to the power 3 halves. Okay. Z is negative d by 2 for 1, but then it's z squared, so the negative it dies. For loop 2, z is d by 2. Okay, and again it's that, so you can see that B1 equal to B2 equal to mu naught Ni R square 2 R square plus d by 2 square to the power 3 halves. And so the net field is 2 times that, which cancels that 2. So the net field at that point is B1 plus B2 equal to 2B1, 2B equal to 2 mu naught and I R square. A superconducting wire of diameter 0.25 centimeter carries a current of 1,000 amps. What is the magnetic field just outside the wire? Okay. So you have these things, so they have a just outside of Philadelphia, they have a superconducting wire carrying a current into the city or something like that. And so that's where you would see an application like this, 1,000 amps and stuff. Okay, so the radius of this wire is 0.125 centimeters. And they want you to find the field outside. Okay, so the field outside, what would be the direction of the field? There. And once you're outside, the field is B is mu naught okay. So mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. I is 1,000 amps, 2 pi, and you're just outside the wire, so 0.125 centimeters, which is 10 to the minus 2 meters. That's 1.25 times 10 to the minus 3, that makes it 10 to the 4 and 10 to the minus 1. So that's 0.2 divided by 1.25 Tesla. Okay. So just outside this 1,000 amp carrying conductor. If a current of 2 amps, how many turns per centimeter must be wound on a solenoid in order to produce a magnetic field of 2 times 10 to the minus 3 Tesla within it? Okay. So you're producing a magnetic field like that. And what is this magnetic field equal to? That's 100 times the Earth's magnetic field. Okay? So the field inside the solenoid is mu naught Ni. Yep. And N is the number of turns per unit length. So N is B mu naught divided by I. So you're producing a field 100 times the Earth's magnetic field. With a 2 amp current. Oh. I knew something wasn't right. and you get 1/meter. So, and that's the units for that, number of turns per meter. Okay, the 2 cancels. So n is, and this becomes 10 to the 4. So 10 to the power of 4 divided by 4 pi per meter. Okay, and they want it per centimeter, and 1 meter is 100 centimeters. C is 10 to the minus 2, that gets killed by that, yes. So it's 8 turns per centimeter, 7.96 centimeters.
Maybe I did my calculator wrong, but I got 78 turns per centimeter.
No, 796 divided by 100 is 7.96. So you hit 10, not 100. Well, you don't even need a calculator for that guy. All right. So toroid has 250 turns of wire and carries a current of 20 amps. Its inner and outer radii are 8 and 9 centimeters. What are the values of the magnetic field at various R's? Okay, so here's a donut-shaped device, and you guys remember, when do you need a field like this?
Fusion reactor?
I'm sorry?
A reactor?
Yeah, so a tokamak is what it's called. All right, now if the thickness of the donut were small compared to its radii, then the field would be uniform. But this is a small donut. So the inner radius is 8 centimeters, and that's 9 centimeters. So you see the thickness is 1 centimeter. That's about 12% the radius. So the field does change. Okay. And what I'm going to do is, I'm going to calculate the field at this radii. And you can do it at any other radii. Okay. So what we'll do is, this will introduce Ampere's law to you. Okay. And so let's say the current is flowing this way. So the current is flowing into the paper. Okay, all those currents. Okay. So now let me just draw this Amperian loop, and the currents are flowing in. Okay. So what we'll do is, we'll go around the loop like this, and the positive currents are into the loop. Okay, so you use your right hand. If you do the line integral along your fingers, positive direction is downwards. Okay, so we'll do the line integral in that direction. Okay, what does Mr. Ampere tell us? B dot ds equal to mu naught I, the total current inside. Okay. Now this is a symmetric situation again. When do we do these integrals?
Symmetry.
When they're very simple to do. You really don't have to do anything. That's when we do the integrals, okay? So b is constant, so it's just b dot ds, and b is constant, and so this is equal to b times 2 pi r, and that's equal to mu naught times I. What is the current threading this loop? Okay, each current, there's 250 turns of the wire, and so 250 turns of the wire, and so there's 250 of those wires going in. So the current is mu naught times 250 times 20 amps. Did you guys understand that? All right, so now the magnetic field is this. So let's see. So the magnetic field is mu naught times I divided by 2 pi r. So mu naught is, and so for all the other radii, all you have to do is change the radii. 4 pi times 10 to the minus 7 Tesla meter amp. I was 250 times 20 amps. 2 pi times 8.1 centimeters into 10 minus 2. So the field at the 8.1 radii is that becomes 10 to the minus 5, and we'll take 3 from here. No, 10 to the minus 5, we'll just take 2 from here, and 10 to the minus 3. So 2 times 2.5 times 20 times 10 to the minus 3 Tesla divided by 8.1. Okay. And at any other radii, all you have to do is change that to that. Okay. So let's find the field at 8.9 radius. So all you have to do is multiply this by 8.1 and divide it by 8.9. Okay. So it's 11 point. Okay, so you see the field is changing about 10% from the inside to the outside. Okay. All right, guys.